Hello, hello, hello. This is Nicholas, and I wanted to talk about special integrating factors for exact differential equations. In the last video, I talked about exact differential equations and the mixed partials being the same, and that's the condition for exact differential equations. But let's say we have m of x comma y dx plus n of x comma y dy equal to 0, and partial m with respect to y is not equal to partial n with respect to x. So this equation would not be exact. But let's say we multiply through by an integrating factor, mu of x comma y. We multiply by this special integrating factor, and there's two separate cases here. And now we claim that after we multiply by this integrating factor, this new differential equation is exact. That would mean, well, we have two cases here. Mu can just be a function of x, or mu can just be a function of y. So let's first consider mu as just a function of x. So basically what I'm going to do here is I'm just going to take this here. I'm going to do this. Oh, I meant to copy it. Oops. Take this, copy, paste. Okay, and now, now I got to move this. All right, and I'll just put this away until later. Because now I'm just going to do this. Ready? This is pretty cool. Just get rid of the x. Just get rid of the x. Okay. So now this means that partial y of mu of x times m, I'll just write it as m for now. I don't want to get it with the xy. I don't want to make it longer than it has to be. Needs to be partial with respect to x of mu of x times n. So for it to be exact. So with respect to y, mu of x is a constant. So mu of x times m sub y, the partial of m with respect to y, needs to be equal. Now here we have to use the product rule. That's mu prime of x times n plus mu of x times n sub x. And so solving for mu sub x, we can get that. Well, first of all, mu of x m sub y, I'll write it like this. Mu of x times m sub y minus n sub x is equal to mu prime of x times n. So mu prime of x over mu of x is m sub y minus n sub x over n. And if I integrate both sides, I get that this is just natural log of mu of x is still we don't know what this is, so we'll just keep it like that, m sub y minus n sub x over n. And so mu of x, the formula for the integrating factor is e to the integral of m sub y minus n sub x over n. Pretty cool. If we do this with respect to y, you can either do this, or you can just believe me that it's e to the integral of n sub x minus m sub y over m. And so these are the two special integrating factors that may or may not work, but it's good to have them in your bag of tricks, so to say. The reason why they may or may not work is because what usually ends up happening, see here, this m sub y minus n sub x over n. This needs to be solely in terms of x, and many times it is in terms of both x and y, which can be problematic, but it needs to be solely in terms of x because mu is just a function of x. And likewise, the n sub x minus m sub y over m needs to be solely a function of y, since mu is just a function of y. So I think it's best to do an example. So let's do an example. M y squared plus 2xy dx minus x squared dy is equal to 0. Now, you first, I guess, might want to check for exactness. So let's do that. Partial with respect to x of y squared plus 2xy is just 2y. Oh, ding dong. It's my bad. This is partial with, it should be with, I'm doing it with respect to y because it's a dx. Y squared plus 2xy. So that's 2y plus 2x. Okay, partial with respect to x of just negative x squared is a negative 2x. So this is m sub y, this is n sub x. Let's try first if we take n sub x minus m sub y over m. We take that, that's negative 2x minus negative 2x minus 2y minus 2x over our m, and our m is y squared plus 2xy. So that's negative 4x minus 2y, or negative 2 times 2x plus y over, now if I pulled out a y, that's y times 2x plus y. And look at that, negative 2 over y. So now mu of y is e to the integral of negative 2 over y dy, which is e to the negative 2 ln y, which is e to the natural log of y to the negative 2, which is y to the negative 2, or 1 over y squared. So now when I multiply this equation by 1 over y squared, it's guaranteed to be exact. I don't need to check it for exactness because I assumed it to be exact if this integrating factor gives us solely in terms of x and y, based on the derivation above. So, and this is actually how they come up with these almost exact differential equations. See, all they did here was just divide this whole thing by a factor of y squared. Or I'm sorry, they multiplied it by a factor of y squared. And when before it was multiplied by a factor of y squared, it was exact. And then they multiplied by this factor of y squared, and then it wasn't exact. And so the whole point that we're trying to figure out here is, well, what did they multiply by so that we can undo it, so that it is exact, and then we can use our usual procedure. So let me write it. The original equation without dividing by y squared is y squared plus 2xy dx minus x squared dy equals 0. So now I divide by a y squared, and I'm going to get 1 plus 2x over y. Yeah, that is... I always mess up on the algebra, and it makes me sad. Minus x squared over y squared dy is equal to 0. Now this is guaranteed to be exact, so we can now just say this is... I just picked the simpler one. Actually, I'll go with this one. Pick the harder one, just for the video. So now we know partial f with respect to x is 1 plus 2x over y. So now f is x plus, now I get a x squared over y, because I'm treating y as a constant there. Now I can differentiate both sides with respect to y, and so partial f with respect to, I almost forgot. F is, why didn't you tell me? This is plus a f of y, because we had to add the constant with respect to x, and the function solely in y is a constant with respect to x. So partial f with respect to y is, well, the x goes away, that's 0, and that's a negative x squared over y squared plus f prime of y. So we compare here, we have this being partial f with respect to y. So this whole thing, we're going to set it equal to negative x squared over y squared. Get rid of that. F prime of y is equal to 0. So f of y is equal to c. So our general solution, our function f of xy, will be equal to, it'll be x plus x squared over y equals c. And that is the